Hello and welcome to the electric potential unit of Phys 1201. And in this unit we're going to meet an old friend, potential energy, and from it we're going to develop probably the most important idea of the entire course, which is electric potential. Let's just very quickly review potential energy because it's going to be very important to us here. So let's say I throw a ball up into the air. This should be very familiar. Then we know it starts with a bunch of kinetic energy that gets transformed into gravitational potential energy, and then as it falls back down, it gets transformed back into kinetic energy. And this is because there's a force acting on the ball, the gravitational force or weight, and whenever a force does work, that results in a transformation of energy. And the amount of energy transformed is equal to the work done by the force, where this W sub F is the work done by some force F, and this delta E is some amount of energy that's been transformed as a result of that force doing work. And so in this case, the work done by the weight is equal to a change in the gravitational potential energy. And note that negative sign. This is a little tricky. Look, when the ball is going up, the force is acting down. Force acting in the opposite direction to the direction of motion does negative work. So that's negative work, but the gravitational potential energy is increasing. So delta UG is positive. And so that explains this negative. And this is generally true. So, for example, when weight does work, it's causing transformations between kinetic energy and gravitational potential energy. In this case, you have a spring force doing work. It's transforming energy back and forth between kinetic energy and spring energy. And again, in this part of the motion, as it's going towards equilibrium, the force would be in the direction of motion, so the spring force is doing positive work, but the spring potential energy is decreasing. And so you always need a negative sign whenever you say that a work done by a conservative force is equal to the negative of the change of the potential. And I'll just remind you, conservative forces are forces that don't produce thermal energy, so things that aren't like friction or drag. So now let's talk about that same sort of idea, but with electrical forces. Now, electrical forces depend on position, and we've seen before that when we have forces that depend on position, we're better off using energy approaches than anything else. So here we have a charge, and it's starting out at rest. It's a negative charge. And here are a bunch of positive charges, so it's going to be attracted to them. And I'm going to think of these charges as not moving around, and this one's going to move in response to forces that this one exerts. And we're going to use energy, so we'd better specify our system. It's just all these charges, and let's say there are no other forces doing work here. Then later on, that charge is going to be moving towards these ones. It will have moved closer, and it's now moving. And so what's happened? Well, it's certainly gained kinetic energy, but this system is isolated. And so that kinetic energy must have come from electric potential energy. So we see a decrease in the electric potential energy and an increase in the kinetic energy. Here, the electric force did positive work, right? It was pulling on this charge. As the charge moved that way, the force was in the direction of motion, and so that work done was positive, and the electric potential energy decreased. In a lot of these discussions of potential energy, there's a certain laziness in the way we talk, and we do it because it's a useful shorthand, but if you're not aware of it, it can be confusing. So let me just point it out. In the gravitational example, where we're throwing a ball up in the air, we'll often talk about the gravitational potential energy of the ball. But if you think back to Phys 1101, you may realize that what we actually mean is the gravitational potential energy of the system, which is the ball and the Earth. But We generally think of the Earth as fixed. We're not interested in what it's doing. We're only interested in the motion of the ball. And so we'll talk about it as if this gravitational potential energy just belonged to the ball. Well, very similarly, when we're talking about electrical potential energy, we'll often have a charge that's moving around, and we'll talk about the electrical potential energy of that charge that's moving around. But again, we really mean the electrical potential energy of the whole system of charges, the one that's moving and the ones that are influencing its motion. But we're thinking of all those other ones perhaps as fixed. We don't care about their motions. We're only interested in the motion of this moving charge. And so we talk about the potential energy as if it just belonged to that charge. Now we're ready to define the electric potential. So here is our situation with a moving charge and some other charges that influence it. And those other charges we are thinking of as fixed. They affect motions of charges we're interested in, but we don't really care about them. They are what you might call source charges. And I hope this is ringing some bells from the last unit in the course. And then here is this moving charge. It moves under the influence of these source charges, so we could call it a probe charge. And so we define the potential this way, where this UE is the electric potential energy of the probe charge. That's using that lazy use of language I just pointed out. This is its charge, and this V here is the electric potential. Now, if this is all seeming awfully familiar, that's good. We just finished learning about electric fields, and they were defined this way. And now we're looking at electric potential, and it's defined this way. And look, those look awfully similar, don't they? So let's make this similarity more explicit. If we're thinking about some location in space, there's nothing there. It's an empty location in space, but we want to know how charges behave around here. We could take a probe charge and place it at P. And now we could measure the electrical force on it, and we could measure its electrical potential energy. And once we have those, we can use the electrical force to calculate the field at P, and we can use the potential energy of this probe charge to calculate the potential at P. And notice how I'm using that language, at P. The E field and the potential are properties of this point P. So the electric field and the electric potential are very similar. Neither one depends on the probe charge used to measure them, although the formulas might make you think that they should. Both are just properties of the location in space that you're looking at, and they tell you something about how charges move when they are at that location in space. On the other hand, the E field and the potential are very different from each other. First of all, the E field is a vector, but the potential is a scalar. Second of all, the E field is directly related to forces, which means it can tell you very quickly things about accelerations of particles as they move through this region of space, whereas the potential is directly related to energy, which means it's often a quicker route for finding out about speeds. Whenever we meet a new quantity, it's good to have a quick look at the units, and of course this tells us the units because this is a potential energy, it's in joules. This is a charge, it's in coulombs. So a potential must be in joules per coulomb. But we define that as a volt. And I know this is awful. We use V as the symbol for potential, and we also use V as the symbol for the unit for it. What an awful choice. Sorry, we're kind of stuck with it. I will tend to almost always put a subscript on any potential. So this would be, say, the potential at point A, so that I don't mix up my symbols that are standing for a potential with my symbols that are standing for the units for a potential. Let's start to look at how we use electric potential, because it is, in fact, one of the most practical things you're going to learn about. So suppose we know the potential at two locations, and I don't know how we know it. Maybe we measured it, maybe we've calculated it, whatever. I'm not concerned with that at the moment. And this could be anything. Maybe this is a circuit, and maybe there's a wire running through here, and we've measured the potential at these 2 points. And now we have charges moving through this region. So again, perhaps this is a wire and there are electrons flowing through it. Or maybe this is in an X-ray machine and we're looking at an electron beam that's about to collide with a target and generate X-rays. Whatever. We know, say, the speed of this charge as it passes through point A. And we might like to know what its speed is as it passes through point B. Well, we're going to use energy because remember, all these electrical forces are going to be changing with position, and so Newton's second law isn't going to be so helpful. But what we need to know then is the potential energy of this charge as it passes through these locations. But that's simple. We know the potentials, and so we can just turn that equation around and get the electrical energy of any charge as it passes through those two locations. So let's do this with numbers. Here's our electron beam. It's passing through here. We know the speed here. We know these two potentials. And we know the properties of an electron. So we're going to use conservation of energy. Look, we've run out of symbols. We're using V's for two things. And now these energies are standing for These E's are standing for energies, not electric fields. So you really have to pay attention to symbols and be careful with them. So here we go. We have our initial kinetic energy plus our initial potential energy equals all the same stuff final. And we know that our U's are all QV's. Right? But Q is just negative E, so let's expand this out using that. A half mVA squared, there's our initial kinetic energy, minus EVA, and I'm being careful to make this lowercase and this uppercase. So you should now solve for what we're looking for, which is this, and check it against my answer. So here's my algebraic answer, and look at this. This is the initial, or the final potential minus the initial potential. So this is our change in potential. And change in potential comes up so often that we have a special name for it, which you will have come across. This is what we call voltage. I'm now just going to plug in the numbers, and again, you should check your numbers against mine. And I get 2.83 times 10 to the 6. We know it should be meters per second. Let's just verify that it is. This is fine. Meters squared per second squared, all square rooted. But let's check this part. We have coulombs per kilogram times volts. And a volt is a joule per coulomb. And so the coulombs cancel, and a joule is just a kilogram meter squared per second squared. And so that leaves us what we should have.